Hello, everyone. Is anyone here yet? Not yet. I saw your hand up there, Dennis. Good to see you there. How are things going? I don't know if I can hear you. It's listen only attendees, but hello to you. Good morning, everyone. Just going to give people a couple minutes to get their calendar notification and show up. So we'll get started here in a couple minutes. All right, I'm going to go ahead and get started. Mona, I don't know if you're, I'm going to enable your mic just to be sure you can speak if you choose to. Um, Good morning, everyone. This is our next in a series of discussions around design control. I think people will be entering in as we go along, so I'm going to go ahead and get started so that we have a half an hour to deal with the topic. Thanks for joining me. Hopefully you can see my screen okay. It's showing up, so I think we're in good shape. So today is the second in the series. Last time we talked about requirements management and an introduction to design control. Today we're going to talk about systems modeling or model-based systems engineering as a topic and how it relates to the requirement set that we were talking about before. So that's what the topic is today. I'll record it and we'll post it up on YouTube if you are curious. So we'll send that out in a subsequent email as we go along. So major design control capabilities. We talked about this last time and I'm just a refresher, but essentially when we talk about design control, There are really 5 topics that typically come into the conversation. The first one and the core one is requirements management. How do we construct the requirements? How do we have a decomposition of the requirements that makes sense for different types of design? But almost immediately as we go into that, we talk about systems modeling. And what I like to say is systems modeling is really the positive view of the design. What do we need the design to accomplish? What are the functions that we need the design to accomplish? That is sort of the positive view. The negative view is really risk management. What do we need the design not to do? So critical to getting a complete set of requirements or even a structured set of requirements is to talk about model-based systems engineering. How do we create a functional model, and that functional model being a formal understanding of how the device functions. And so that's what the topic is today. Second thing after we get done with this, and this is really in order, from my recommendation standpoint, in order of priority from a deployment standpoint. First, I do requirements, then I do systems modeling. Standards management would come next. And when I say standards management, I mean external standards management. How does that map into the requirement set? Verification and validation is really our evidence that the device complies with our definition of good. And finally, risk management is that data model that allows us to integrate the FMEAs and the hazards analysis with the rest of the data. So that's what the overall design control model is. And today, of course, we are talking about the systems modeling, which is this 1B aspect of it. So let's just talk a little bit about what is a function, what is systems modeling, and how that relates to requirements management. So if you think about a function as a black box, and we have inputs or inflows to the black box, and we have outflows from the black box. What that function really is a transformation that transforms the inflows to the outflows. And so when we talk about the functions, what we really want to understand is what is that function supposed to be doing? And then from a requirements management standpoint, what we're characterizing are the outflows. And you can imagine that all the inflows are outflows from other functions. So when we talk about characterizing those outflows, we only need to characterize the outflow portion of it, not the inflow portion of it, because the inflows are outflows of another function. So what those requirements do, though, is they characterize what do we mean by a good outflow and provide us with a testable understanding of that outflow. So the outflow might be something mechanical, like a torsion shaft, a shaft torsion, or it might be something related to usability. The device has, the user will turn the device on and off. Okay, there's an interface between the person and the device, and that requirement would characterize what that interface needs to look like. So really the requirements, when we talk about this, and we're going to go into more detail here, the requirements do is they characterize all of the outflows of all the different functions and functional chains. And that's really the purpose of the requirements, to characterize those outflows. Okay, so exactly what is a function? It's a verb-noun combination typically. It's something something is going to do something. That's really what we're looking for. Delivers vacuum, regulates pressure, gets the configuration, sets a digital pressure level, right? So we want that verb-noun combination. In this case, the example we're going to talk about is regulates pressure. So we're going to talk about a function, and that function might be deployed inside of a pump, for example, or inside of a pressure regulator. And you can imagine there's all kinds of different pressure regulators out there, but we're saying we're gonna specify a pressure regulator, and what that function, the function that regulator is going to provide, is to regulate the pressure. So inflows might be something like line pressure at a specific flow rate, or possibly an electrical signal to give you a sense of what the pressure needs to be. So depending on the regulator and what we need out of the system, we'd have different types of inflows. The outflow then, the characterization of that outflow is what we need into the system is a 40 PSI plus or minus 1 PSI at 5 CFM. So what we're looking for as an outflow is different what the inflows are, and what that regulator is going to do is regulate the pressure down to a specified limit. So now we understand specifically at a design level exactly what we need this function to provide. Now, because this function currently is deployed in one component of the design, which is the pressure regulator, we don't really need to characterize it fully. And what we have is an understanding of where that function's deployed from a discipline standpoint. So from when we move to risk management, we can specify and say, okay, this is a mechanical component of the design, and that function needs to be delivered by the mechanical engineer and will be processed through the mechanical FMEA structure. So at this level, we really need to understand what discipline it is so that we can push it through the correct set of FMEA activities. So that's kind of what we're doing here is we're saying we have one component of the design, we have a function that's delivered by that. How do we characterize it? Now, let's say we did some risk management and we found out, this thing that's coming out of the box, the pressure isn't regulated well enough to control a problem. And I'll just give you an example of this. When I worked in the eye industry, we had a vacuum system that would sit on the surface of the eye and fixate the eye. So it might be one thing for if we're using pressure and we don't care if it's plus or minus 5, we could get that off the shelf. But if we have this harm that's associated with rupturing the eye globe, we might need much better control of that vacuum source. And if that's the case, what we need to do is think about this now not as an individual component, but as a system that's going to require closed loop control. So what we're going to do here is we're going to blow this out and say, okay, this one function is now a system. And what we're going to do is, again, we're going to deliver the vacuum. We're going to regulate pressure. This is what the functions are. And we're going to define the delivery of the group of functions delivered in more than one component of the system. So now what we're doing is we're taking that regulator and we're breaking it up into a print circuit board. We're going to have a pump, we're going to have a proportional valve, we're going to have a sensor, whatever is required, probably software, whatever is required to provide that closed loop control so we can get better outflow control. So chain defined by inclusion of the functions in a group. So what is a functional chain? A functional chain is a set of functions that go in sequence across multiple components of the design. So by definition, when we have a system requirement, what we're doing is we're characterizing the outflow that's delivered by the functional chain, not by any individual function. So again, it transfers the inflows into the outflows. So we have this line pressure coming in. We have an inflow that's the desired pressure. And then what we can do is we can get more granular control over what that outflow pressure is. And so this requirement then that we're writing against the pressure regulator is now a system requirement because the outflow is the outflow of the system, which is delivered by the functional chain. And so one of the things that we need to get into our head as we're starting to write requirements is really what is the difference? What's the formal difference between a design requirement, design level, and a system level requirement? When we say a system level, a lot of times what I see in industry when we write these system requirements, you might say something like the system needs to be compliant with a ISO document. Well, when you write requirements like that, what you're doing is you're characterizing not the function of the device, but compliance with an external standard. What we need to understand is those system requirements. The purpose of writing the system requirements is to understand what the system is delivering in its components and then as it's stacked up in systems and subsystems. So we're really trying to understand functionally what does it need to do, and in that chain, what is that chain designed to deliver? So in this case, the chain is designed to deliver more control over the outflow, but each one of these functions now, as they're delivered in components of the system, are going to have different outflows that are going to be delivered by a particular discipline. So we might have a mechanical do the pump, we might have an electrical design do something around the PCB. So depending upon what we're talking about, whether it's software, hardware, usability, whatever, at that point we would have the component identified and we understand what discipline to push the FMEA through. So this separation is really important to being able to understand how to write our requirements. So hopefully this is clear. And again, all these outflows are different outflows for the design. And the red line, I think I said this, but the red arrows represent the functional chain as it goes across those different components. So the next question is really, what is a product capability? And the reason I'm going to talk about this is we're going to start talking now about the specific systems modeling tools and how they work. A capability is a level above the functional chains, and what it defines is something that's delivered by the system. And so when we think about traceability from the product capability, what we're really talking about is traceability to the user needs. So the user needs the system to deliver a capability. That capability is defined in the systems model as a product capability. And one of the things that I run into a lot is, people don't like terminology. Really what I'm saying is that the Arcadia method that's deployed in Capella, which is the tool that I'm going to show you here in a minute, defines these terms this way. So when you get into the tool, it's going to say, what is a capability? What's a functional chain? I'm just using the formal language that the application is going to give you, so it's clear to you when you get into the application. But when we provide traceability then to the requirements, the product capability transfer or is related or linked to the user need. The functional chains are linked to the system requirements, and then individual functions as delivered in one component of the system are delivered with design requirements. And oftentimes there's going to be multiple outflows, and maybe you even need more than one requirement to characterize any particular outflow. So it's a one-to-many relationship between each one of these. Okay. I just wanted to mention this because as we get into the modeling, you're going to see these different levels. And so the way this works, the way the Arcadia method works, is we have 4 different levels of abstraction to go through the design. We start at the operational level, and this is really an analysis of the design space. We don't really have an understanding yet of what it is that the device is going to do that we're going to sell. The device that we're selling goes in the context of the overall system. And the first thing we want to do is just get a clear understanding of the design space. The second one is, the system level, and here it's called functional, non-functional need. The system level, what it does is it breaks the device that we're going to develop apart from operationally the entire design space. So in the operational analysis, we would have a set of activities, and in the systems level, those activities become functions, and we start to say, okay, functionally, what do we want our device to do versus what functions exist in the design space. And so one example of that is entities like nurses, patients. We aren't selling anybody a nurse. We're selling them a device that the nurse interfaces with. So we need to understand what the nurse is doing and what the device is doing. Then we take that down a level and we abstract that to a logical level. And so we might say something like, we have a containment device, or we have something that creates vacuum. So logically, we're trying to say how the device works together, but we haven't physically understood what the embodiment's going to look like. And then finally, we get down to this physical architecture level where we're identifying printed circuit boards, sensors, interfaces that are not abstract, but they're, we have a USB interface here, we have a cloud interface here. So once we get down to that physical architecture, we can actually do risk on it because we understand what the discipline is and what parts are associated with any of the analysis. So I'm going to walk you through these levels in the systems modeling tool so you have a better sense of what it looks like in the application. But just know that we're going to go down 4 levels to get to that physical architecture. And this is a method. One of the things that you really struggle with in systems modeling, depending on the application you use, because there's a bunch of them, Rhapsody and NoMagic, and Capella is a different one. But Capella, what it does is it embodies the Arcadia method. Most of the systems modeling tools are a set of diagramming tools, but they don't really have a method to walk you through the development of the design. And I think this is a really useful way to do it, just to understand from an engineering perspective, how are we doing this? How does this progression happen? So the first thing we do is a capability diagram. And as I said, we're at this operational level. We're going to look at the overall design space. This example was one we built at Siemens from the open source PB560 data that Medtronic made available during the COVID crisis. So we developed a whole set of models around this. So what this does is say, if we're going to do ventilation, what needs to happen? You know, we have a hospital system, we have a patient, we have clinicians, we have a ventilator manufacturer. What are the capabilities we want to deliver to provide ventilation to a patient? So there's, you know, we want to monitor the operational status, support the hospital call system, but one of them is this deliver ventilation. That's one of the key aspects of a ventilator is to deliver the ventilation. So what we're going to do then is we're going to further break that deliver ventilation down to understand what other kinds of capabilities are required to do it. And so we're going to have different modes. We're going to have constant pressure airway with an exhale assist. So these are the different capabilities. To deliver ventilation, we're going to have some capabilities in the system to provide that kind of functionality. So again, we have deliver ventilation. Now we're going to go down a level and we're going to do an activity diagram. And what this activity diagram does then is goes through what are the steps that we're going to have to accomplish to deliver that ventilation. And this is the first place that we start to see this terminology, this ability to create functional chains. And at this level, the chain it's a very high level discussion of what we're going to do. And we have these different aspects. And again, we have deliver ventilation. And what we're saying is we're going to have a functional chain that shows what deliver ventilation means. So we're going to connect to the patient. We're going to deliver ventilation to the patient. We're going to convert air to blood oxygen, monitor the patient respiration. At a high level, this is essentially what we are going to need to do to deliver that ventilation. So then when we go down to the system, this is where in my opinion, it starts to get more interesting, is we're now breaking the ventilator out from the rest of the system. And we're saying, functionally, what do we want the device we're selling to provide us? And that device is going to have different aspects to it. So as an example, we're saying in this case that monitoring the patient vitals is going to be done as a process by the clinician in the room. It's not going to be done by the ventilator. And so just as an example, if we wanted to break pulse oximetry out from this vitals measurement and put it in the device, we would have a box here that would say, functionally, we need to measure the oxygen level of the patient. And then that function would be interrelated with the rest of the functions in the device to decide what we're going to do with that data. How is it going to, what are the algorithms it's going to take advantage of? How is it integrated with the device itself? But in this case, because it's delivered by the clinician, it doesn't have anything to do with the ventilator at all. And so these are the decisions at the design level that we start to make, is literally what's in the box, what's out of the box, what's in the device we're selling, and how does that relate to the design space in general. So when we do that, then we have this deliver AC mode down here. And what we're going to do is more fully evaluate this green functional chain so that we have a clearer understanding of physically, first logically, but then physically how it's delivered. So when we go down to this logical level, now what we've done is, instead of just saying we have an overall system, what we're doing now is we have a patient ventilation system as an abstract concept. And what we're starting to do is say, okay, how would we construct this logically if we wanted to? So we're going to have an air generator, we're going to have an O2 valve, we're going to have a housing, we're going to have a user interface. Not saying, what kind of a user. Is it going to be buttons? Is it going to be touchscreen? We don't know, but what we do know is the patient's going to have to start and stop the ventilation, and they're going to have to interface with the system somehow. And so that's really what this is allowed, provides you with, is a middle step between the physical architecture and just, we have this abstract system out there. Now we're saying, okay, logically, how would we break this device up to have a better understanding of, what we need to do from a physical architecture standpoint. So again, we have this deliver AC mode as a functional chain, and that's the blue functional chain. So we get a further decomposition down into this third logical functional level. And again, that start and stop ventilation. One of the things that's really, I think, interesting is when we talk about usability engineering, what we're really doing is we're saying, what function does a person in the system do to deliver something to the system? Once we understand the function that they're providing, this interface line to the user interface is the thing that we're going to be evaluating in a usability FMEA. Under what conditions do we have a perception and a cognition error that leads to actions that are inappropriate for this specific function that the user is supposed to be delivering to the user interface? That's the axis by which we would do that analysis. It's a very different way of thinking about how do we identify what is the user doing and how is it interfacing with the system. We don't need to look at everything. We just need to look at the functions that user is delivering and how that can go wrong. This diagram actually almost perfectly matches the 62366, med device usability standard. So kind of an interesting aside there. Okay, so now we get down to the functional layer. And at the functional layer, this is where we're going to start talking about the characterization of the requirements and also risk, because now we understand how the thing is deployed. At this level, now we're not talking about abstract concepts anymore. We're talking about, we have a PCBA, we have a ventilator software, we have a buzzer, we have turbine control, PCBA, so we know exactly physically how this is going to be developed. Now, one of the tricks of this in systems modeling, these components of the design are delivered with the bill of materials in the PLM system. So one of the things you want from a traceability standpoint is a direct traceability from the components of the system to the bill of materials. So we understand in the bill of materials how this is realized. And now we have the outputs established as a traceability to the components of the design. Very important for reporting later. So we have this very clear understanding now physically of how it's deployed. One of the things that we want to be able to do then, if we look at this system requirement right here, the system requirements are now related to these functional chains. So the question you have to ask yourself is, this blue functional chain, if it works properly, what is the outflow of that chain? It's a different question than the second thing, which is really this design requirement outflow. So we have generated the airflow. We have an outflow that goes into the lower housing. That outflow characterization is the design requirement, right? And you can imagine that when you're writing those requirements, these design level requirements are very different, and they're also, it's identified because the function's deployed in a component of the design that is discipline specific, that's going to be deployed and characterized by the engineer that's associated with it. So you can imagine if I have breath delivery and I have an outflow from breath delivery, that outflow is going to be characterized by a software engineer. If I have a turbine and that's a mechanical component, the outflow there is going to be determined by a mechanical engineer. But the overall system and the way that's characterized is multidiscipline. And that's really going to be characterized by the systems modeling people, right? What do we want this functional chain to deliver? That really has to do with a multidiscipline delivery of that particular process. So that's important, because as we go into requirements management now, what we're going to do is roll over, and I'm going to talk to you a little bit about this design requirement. So we have generate airflow, right? Is this design level function, and I'm going to be writing requirements then in Polarion. Generator airflow becomes a function that's delivered, and then each one of these requirements then characterize the outflows of that particular function at the design level. And of course, we'd have another one that is the functional chain for the system requirements, and they would characterize the outflows of the functional chain. So hopefully this kind of makes sense. What we're trying to do is use the systems modeling to develop a formal understanding of the functions. Once we do that, then we have a very clear picture of all of the different requirements that need to be generated from the system. So when are we done with these requirements? And I think really one of the key aspects of this is you're done when all the functional chains and design requirements have at least one requirement and outflows are fully characterized. So if we need more than one requirement per, that's fine, but we need at least one for each one of these functional chains or functions that are deployed in the system so that we have a full characterization of how it's done. Okay, so that's really what functional modeling is all about, is getting to a place where we understand what is our definition of good and how do we characterize appropriate testing. So what's the value? Yeah, and then ever had that gnawing feeling? So when you're in these designs, you don't really understand how it works. The Boeing disaster is a good example of this. We had sensors, we had pilots, we have software, and what happens is as we make changes to the system, we don't really understand how those different things interrelate with one another. So when we make a change to the system, we don't create duplicity in the sensors, or we use software at the wrong altitude, or we don't have the appropriate training. And what happens is the system breaks down because we made a change to a functional chain and we didn't understand the implication of that. And so this is something in complex design that happens all the time. And getting to a place where we really understand how these things work together is super important to delivering the kind of functionality we want for our patients. What does that complete set of requirements mean? Now we have a real definition of when we're done. And if the device fails, exactly what needs to be changed. So it's all in front of us. The requirement set is there. The risk management will be there. And then we have a functional understanding of how the device works. So we have all of the impact of any particular change right in front of us. Eliminates that requirement subjectivity. So if you need some help with this, I'm happy to help. This is my information at the end here. So we have a design control registration link if you want to send that to anybody to register for the next session, which I think is external standards management. Or schedule a meeting with me or my LinkedIn account, or you can subscribe to the YouTube channel to get this content. Feel free to do that. I'm looking to get 1,000 people on there so I can do my webinars on YouTube. So welcome to Lunch with Larry. Thank you for the day. And I don't see any questions that have been posted. So thanks for attending, and we'll talk to you next time, which is Thursday next week, by the way.